Today we begin Unit 2, where we're going to be focusing on Newton's laws, specifically how forces interact with bodies that are either stationary or moving. So lots of interesting problems. Newton's laws really revolutionized physics and in the late mid-1700s. So we'll be learning how to apply his laws to several different situations. So key concepts today, we're going to focus on Newton's first law. There are three laws that we call them three Newton's laws, and then there's a universal law of gravitation. So there's four altogether. We're going to focus on the first one today. So we're going to talk about what is a force, what is a net force, and how is that different from just a force. What happens when a net force is zero. And then we're going to look at analyzing forces with what we call free body diagrams. So you'll get a little practice with that. Quick little history though. Aristotle, who lived in 384-ish BC, was the first one to try to describe motion, and he called what he described as natural motion. The idea is that an object that's not in its proper place is going to try to get there. So a lump of clay would fall to the earth because that's where it belongs. Clay belongs on the earth, and a puff of smoke, being of air, would float up. So natural motion, he believed, was straight up or straight down. That's the way things would behave if left to their own devices. And then he said there's violent motion. So violent motion is what happens when you're actually pushing or pulling and causing something to move. So pushing a cart, lifting a weight, hurling a stone. These are externally caused events. Some action is incurred to create some motion. So except for the celestial motion, the normal state of motion is at rest. And I say except for celestial motion because they knew that the heavenly bodies were moving. The Earth does not move, according to Aristotle. In other words, Earth was fixed, and the stars and the planets and everything they were observing, moving in the celestial realm, was all moving around the Earth. And the understanding was that there wasn't anything big enough to move the Earth anyway, so it couldn't possibly be moving. So we move into now Unit 2, and we talk about why objects move. In your textbook, you look at section 4.1 and 4.2. That's a really good read to get you some good background. So why object moves were based largely on the work of Galileo. And Galileo was working on the heels of Copernicus. And remember, Copernicus was the scientist who described the fact that the planets revolve around the sun instead of around the Earth. So that was a huge leap in the understanding of heavenly bodies and their motion. So Galileo came up with what's called the law of inertia, which is basically Newton's first law. So we're going to talk about that extensively today. Then Isaac Newton took the work of Galileo and then built upon it and came up not just the law of inertia, which is Galileo's, but his two additional laws. So the first law of motion, which is also known as Galileo's law of inertia, is one you've heard before. A body at rest remains at rest unless acted upon by an outside net force. And then a body in motion is going to remain in motion. So, force. What is a force? A force is going to affect motion. It's a push or a pull. It can cause motion, just as Aristotle understood this violent motion, so that's what forces are going to cause. It's an action that creates some sort of movement. And Aristotle's biggest mistake in thinking about motion is this natural state of rest, because he didn't understand the notion of friction and how friction was a force that was causing things to slow down. So it wasn't until Galileo that we started to understand the notion of friction. We have two different kinds of forces we categorize. We call them contact forces and field forces. Field forces are forces that act from some distance away. Remember, forces are vectors. So like displacement, velocity, acceleration, they have both magnitude and direction. So you can have a big force pushing in one direction and a little force pushing in the other direction. So contact forces, push, pull, kick, tension in a string. Friction is a contact force, and then normal force. We'll talk about those, but a normal force, think normal like perpendicular line. Normal force always acts perpendicular to a plane of contact. And then field forces are forces that act from a distance away, and they were very difficult to understand for people like Aristotle. It wasn't until Newton came along that we really did begin to understand these. And those include forces like gravity and electrostatic forces, repulsion, and attraction, magnetic forces. And then at the very end of the year, we'll be learning about the strong nuclear and the weak nuclear force. Those are both field forces. SI unit for force is the Newton. The Newton was named after Sir Isaac. It is also known as, well, if you want to break down a Newton is its own special name, but it stands for a kilogram meter per second squared. So if you want to break it down to its SI components, but we say the SI unit for force is newtons. Okay, so today we're going to look at problem-solving scenarios where the sum of the forces is 0. So you'd say there's no net force pushing on something. We call that situation static equilibrium, meaning it's at rest. Static means at rest. Equilibrium means balanced. And then the other situation is called dynamic equilibrium. So equilibrium still means it's balanced, except this time dynamic means it's moving. So you can actually have a sum of your forces be equal to 0 on a moving object. And we say that moving object is not accelerating, but it's moving at constant velocity. So you can have a block sliding along at constant velocity with no net forces. We write that in mathematical terms, the summation sign, sum of the forces with a vector is equal to 0. So equilibrium, what we're talking about is sum of the forces is 0, there is no net force, in that case the velocity is constant, and there is no acceleration. A body is at rest will stay at rest, and a body is moving will stay moving at constant velocity. In other words, it's going to go at the same speed without changing direction, as long as there is no net force acting on it. We'll use free body diagrams, which is where you isolate an object and you look at all of the forces that are acting on it, and you think about what is happening. So we're going to draw all forces acting on an object. So for example, if you have a block here on a table and you have a rope pulling the block is at rest, so it's not moving. So you would make a little sketch of all of the forces acting on the block. And so what we do is we isolate the block itself, and we're going to think about what are all the forces acting on it, and we're going to break it down into the x direction forces and the y direction forces. And when we're doing a free body diagram type of statics problem, we know that the sum of the forces in the x direction have to equal 0, and the sum of the forces in the y direction have to equal 0, because the block is not moving. So then we go ahead and draw all the forces. Typically, if you have a block in a gravitational field like we have here on Earth, one of the forces is going to be the force of down. We call it F sub g. That's the gravitational force. That's essentially the weight of the object. In this case, we had the rope pulling, so we have a tension force that would be pulling to the right. And then finally, if the block isn't moving, you know there must be friction that's holding that block there. So then we'll have a friction force that is acting to the left. Finally, because the gravity force is pulling that block down, and that block doesn't move, something must be pushing back on it. Something must be holding it back up. And that thing that's holding it back up is the normal force. So that is perpendicular to the surface, and that's going to keep that block where it is so it doesn't go falling through the table. So if you look at these little vectors, and the size of the vector represents the magnitude of the force, you see that these arrows here are equal and opposite. So if you add up the forces in the x direction, they're going to cancel each other out. Same thing with these guys. Okay, the forces in the y direction, you have a positive force and a negative force, and they're going to balance each other out. So other scenarios with free body diagrams, if you have a situation where you have like a little ball and it's hanging from a thread, then we're going to get rid of the thread and isolate the ball and think about the forces acting on it. So we're going to have a gravity force pulling it down, and we're going to have a tension force pulling it up. Obviously, these are really simplistic problems. They're going to get more complicated really quickly. And then we have this problem over here. We have a block that's resting on a ramp. So here's a block on a ramp, and you might be holding it up, or it might not be sliding because there's friction. So you look at all the you isolate the block again, you look at all the forces acting. You're going to have a gravity force, and the gravity force is going to be pulling straight down towards the center of the Earth. So you can just get the habit of that. Whenever you're doing a free body diagram, you can have gravity going towards the center of the Earth. In this case, you have a normal force that is perpendicular to the surface of the block. So it is not in the same direction as the gravity force, but it's pushing up and parallel to the perpendicular to the surface here. And then finally, you're going to have a friction force that's holding that block so it's not sliding down. And you can see that this problem becomes a lot more complicated when you want to consider what are the forces in the x direction, what are the forces in the y direction, because they're not all in the same angle. So we're going to have to do a little trig for that type of problem. Those are pretty challenging. Okay, so here's an example problem. Let's work it out. An owner is pulling on her dog with a force of 70 newtons, directed at an angle of 30 degrees to the horizontal. Draw the free body diagram of the dog. And then find the x and y components of the force vector. And we're talking about the force vector of the person pulling on the dog. So, here's our free body diagram of a dog. We don't try to get too fancy and draw cool looking dogs, mostly because I can't draw cool looking dogs. So we just create a little block. And we show that we have a force, and that force is acting 30 degrees from the horizontal. Now what we want to do is indicate all of the forces and the values that we know. So we have 70 Newton force pulling up at an angle of 30 degrees. We want to break that 70 Newton force. Oh, if I want to do the full free body diagram, then I would probably have to add one more force. I should have a normal force as well. So there's our free body diagram with all the forces acting. Okay, but the problem says find the x and y components of the force vector, meaning this 70 Newton force vector. And so we want to find what's the y component, what's the x component. We're going to use trig just like we've been using. So we're going to say the cosine of 30 degrees is adjacent over hypotenuse, which is fx over 70. So we can solve to get the fx is 61 newtons. Then we'll do the same thing for the y. 70 times the sine of 30 is going to give you the y. So you're going to have to get good at taking forces given angles and breaking them into their x and y components. And with a little practice, you'll get really good at it. Okay, which of the following forces is a field force? Quick little concept question. When I throw these at you in a virtual lecture, just pause the video, think about it, and then I will give you the response. Okay, so I hope you'll see that normal, normal, tension, and friction are all contact forces, so the only remaining field force is magnetic. All right. So what is a net force? When you add up all of the forces on the object and you combine them, the net force is whatever's left over. So in the case of this block that we show you right here, I have a 30 Newton force acting to the left. Now I'm going to define to the right as positive, and so I'll say positive 20 Newton to the right, negative 30 Newton to the left. If I sum up the forces, I'm going to get a net force of, in this case, 10 newtons. Actually, it's going to be a net force of negative 10 newtons. Okay, let's talk a little bit about Galileo. Galileo argued, and he was the first one to do this, that only when friction is present, as it usually is a force needed to keep an object moving. So a little bit more of his kind of argument, and then we're going to think through how he thought through. Friction is the name given to a force that acts between materials that touch as they move past each other. So we have little irregularities in surfaces as these irregularities interact, and it's basically an electromagnetic irregularity interaction. It causes the objects to find some resistance and to kind of slow down. But if we consider what happens if friction were absent, then an object that's moving is going to keep on moving whether there's a force or not. So he tested his idea. So some of these he tested actually experimentally, and some of them were more like thought questions, so that he considered what would happen and then kind of came to the conclusion that an object in motion will remain in motion. So what he said was, he rolls balls down a plane surface at different angles. Let's look at the next one. So here's the idea. If you start rolling a ball, it's going to move because of the gravitational force of Earth. So it starts moving down the slope, and then it will be moving up and slowing down. And if there's no slope, then it would make sense that because it goes faster on the way down and slower on the way up, that if the surface is fast, that the speed wouldn't change. That's just sort of a logical argument. The other idea is that if a ball is moving horizontally, it's going to go forever. And so here's another new line of reasoning. He had two inclined planes, so I'm going to show you the pictures. The idea is that for the first one, if he rolls the ball down, it's going to come down, travel across, and then come back up. And the height it achieves is going to be the height of whatever it was at its initial position. Now, if you make that ramp successively longer, so that you might decrease the angle and it has to go further, it still is going to achieve its final position. So if you keep taking this ramp right here and making it a shallower and shallower and shallower angle, eventually you're going to get to the point where you have a horizontal, and you say, well, where's the ball going to end? Because it can't achieve its final position. Well, the idea is that it's going to go on forever and ever without ever stopping. So another cool logical argument that Galileo put together. So he said this tendency of an object to keep moving is natural. That's the natural state of motion. Every material object resists change to its state of motion. And that concept is described with the word inertia. So something has inertia means it's resistance to changing movement. So if it's standing still, it wants to stay still. If it's moving, it wants to keep moving. All right, so here's another practice problem. A book weighs 12 newtons, is at rest on a table while a person is pushing down it with a force of 4 newtons. Draw the free body diagram for the book and find the normal force of the table on the book. All right, so here we go. This is how you do a free body diagram. So first, this is a little schematic of what's happening. You have a book on a table and you're pushing down on it. Okay, that's not the free body diagram. That's just a sketch of what's happening. Free body diagram, I isolate the book and I just draw the forces. So I have a 4 Newton force down from the person pushing. The 12 Newton is the weight of the book, so that's pushing down. That's the gravitational force. And then you're going to have a normal force that's pushing up. And you can imagine, like if you were the table feeling this book, it wouldn't feel so bad with just the book lying on top of you. But then if someone starts pushing on it, you're going to feel it and you're going to push back. So that's the idea, that the harder that hand pushes, the more the normal force is going to be. Now we're going to solve it mathematically by saying the sum of the forces in the y direction is equal to 0. And now we're just going to list them all and figure out what that normal force is. I'm going to define up as positive. So I'll say that the normal force, which is in the upward direction, okay, minus this 4 Newton force, because that's in the downward direction, minus the 12 Newton force, which is also in the downward direction, is equal to 0. So minus means the same as plus and negative because the vectors are negative. So I solve and get the normal force is 16 newtons. Newtons. There we go. Oh, okay, good. Okay, so mass and inertia are pretty synonymous in physics, okay? Mass is the way we actually quantify how much inertia something has. Inertia, remember, is a resistance to change or resistance to change or move. So the law of inertia, which is Newton's first law, is that objects don't like to change their state of motion. A body in motion remains in motion unless acted upon by an outside net force. Okay, mass is a fundamental quantity that we can measure. So here's some examples of kind of Galileo's idea. A body at rest tends to stay at rest. So here comes the dog, and the dog thinks about a cat, and the dog takes off and pulls the wagon right out from under the kid. The kid doesn't move, although the wagon maybe does. So the kid stays at rest. So there's your example of a body at rest. And then here's your one about a body in motion. Okay, body in motion tends to stay in motion. So that truck, once it gets moving, is not going to be easily stopped. It has a lot of inertia because it's a big, massive truck. Okay, so go ahead and pause the video and figure out the answer to this concept question. Okay, hopefully you figured out that all 3 of these are true, so the answer is all of the above. Another concept question, law of inertia applies to moving objects, objects that are not moving, both moving and non-moving, and of course the answer is C. Okay, mass and weight. So this is a common confusion to people who haven't taken physics. People say confuse mass and weight and think that they are synonymous, but they are definitely not. In physics, we measure mass in terms of the SI unit kilogram. You've done a lot of grams measure in chemistry, so we use kilograms in physics. So mass is measured in kilograms. Weight, so when you step on a scale and you find out your weight, that's actually not your mass. That is a force. And your weight in English units is in pounds. If you want to find your mass in English units, it would be measured in slugs. And so you don't really have scales using English units that are slugs, but we do have, you know, our little scales in our physics lab that are measuring grams and kilograms, or parts of a kilogram, and those are definitely measuring mass. Mass is not going to vary no matter where you are. So your mass on the Earth is going to be the same as your mass on the Moon, is going to be the same as your mass on Mars or in outer space or wherever you are. Your mass is inherent to you. Your weight, however, is going to depend on the acceleration of gravity. So your weight here on Earth is significantly larger than your weight would be on the Moon, where there's much less gravity. In fact, there's 1/6 the gravity on the Moon, so you would weigh 1/6 what you do here on Earth. To get the weight, all you have to do is multiply the mass times the value for gravity. In this case, we do the gravity that is here on Earth, which is 9.8 meters per second squared. So mass is the quantity of matter of an object. So it's basically a measure of inertia or laziness. In other words, if you have a big, heavy object, massive object, it's going to be hard to get it to move. Weight is the force of gravity on an object. So F equals mg. So when we talk about the gravity force, we say F of g is equal to whatever the mass of the object is times the acceleration of gravity. And the SI unit, as remember we talked about force was in Newton, and we see how it's kilograms times meters per second squared. So Fg is mass, which is kilograms, and gravity is meters per second squared. So that's where that unit is coming from. Another concept question, go ahead and pause the video and answer it. The answer here, of course, is C. Balls moving horizontally would move forever. Otherwise, they're not going to slow down. Okay. Keep going. Block is being pulled at a constant velocity by a horizontal rope of tension 5 newtons. The net force on the block is what? Okay, so this is a little bit of a trick question. Pause the video and take a look and read it very carefully and think about your answer. So you might be tempted, seeing this, to think that the net force is 5 newtons. But there's a key word in here that describes why that can't be true, because it's being pulled at constant velocity. So if something's being pulled at constant velocity, that means that the sum of the forces has to be 0. It's not accelerating. We call this dynamic equilibrium. So if the sum of the forces is 0, then we have a constant velocity situation. Therefore, the answer is C. Okay, this is a trickier question. If the blocks below have the same mass, in which case will each rope have the greatest tension? So this one you just kind of think about, and think about what makes most intuitive sense to you. Like, if you have the ropes pulling straight up, is the tension going to be less on the ropes? Or if you separate them like you do over here, is there going to be more tension? So which case? And use your intuition, because it's pretty good. So the idea is this. If you take the block on the left, you're going to have an mg force down, which means that each rope is going to have half of the mg force that it has to support going up. And all of that force is going to be in the tension of the rope, so mg over 2 for each rope. But if you start spreading it out, and you go with this one over here, then you realize that the vertical component has to have that same mg over 2 in order to hold up the block. But if the vertical component, those two ones, have that, then you also have this sort of pull apart, like yanking them separately horizontally. You have these horizontal forces that are also acting. So the total tension, which represents this vector right here, let me make it yellow, this is your tension force, is going to be significantly larger because it has to deal with the combination of the upward force that it needs to hold the block and that separating force. So this is going to be a much higher tension for part D. Okay, another practice problem. Box weighing 2 newtons is suspended by 2 ropes, which each make a 45-degree angle with horizontal. Draw the free body diagram for the box and find the tension in each rope. This is really similar to the type of problem you have in your homework. We start by sketching in the block and drawing all of the forces that are acting on it. We have a rope going off at 45-degree angles. The block weighs 20 newtons, so we have a force downward. And then we're going to have our what we call those tension forces, and we want to figure out what is the magnitude of those tension forces. If I want to break down that vector, the tension force vector, I'm going to have a horizontal component and a vertical component. So I've got Ft cosine 45 is going to give me the horizontal component of one of those vectors, and Ft sine 45 is going to be the vertical one. Again, I just used trig. Cosine of 45 is adjacent over hypotenuse. Okay, so that's how I work that to get those two components. So now I'm going to do some of the forces in the x direction and the y direction. So if I go in the y direction, I've got the Ft sine 45, that's the vertical component for one of these guys, so there's Ft sine 45, and then I've got the one for the other guy, and then I've got the gravity force acting down, which is minus 20 newtons. The other two are positive. And so now I have a little equation, and I just have one unknown. So I can go ahead and solve for S of t, and I get F of t is 10 over sine 45. Now this particular problem didn't ask me to figure out what the x component of the force is, so I didn't need to do that, but I did solve and find out the total magnitude of that tension, which is 14 newtons. Okay, now I'm setting this up for you. We're going to do these problems kind of down the road, but ramp problems are definitely more difficult than the other types of problems we're going to say. So here's the idea. We have a block that weighs 40 newtons. It rests on a frictionless ramp inclined at a 30-degree angle, held in place by a rope. So we're going to set up the free body diagram for that. Here's the idea. You have a block, you have gravity pulling straight down, and you have it's a frictionless ramp, but you have tension. So you have a rope holding it on the block and a ramp at 30-degree angle. So what we're going to do, the trick to solving ramp problems is to come up with your x and y axis. We're going to do a sum of the forces in the x direction, sum of the forces in the y direction, and to have the x axis parallel to the ramp itself. And then the math gets a little bit easier. So here's the trick. That mg force, we have to break down that gravitational force into two components. One that is parallel to the ramp, so that's going to be this one right here. And then one that is perpendicular to the ramp, and that's going to be this one right here. And once we get those components, then we can set up our equations. So I break the mg. If you look at your triangle trigonometry, there is going to be a 30-degree angle right here. That's going to be a 60 over there. So you get you're going to get mg sine 30. Okay, that's going to be in the x direction, minus the tension of the rope is going to be equal to 0. So now you can solve for the tension, and you're going to get tension is just mg sine 30, and we're already given the mg, which was 40 newtons. And so it should be, ooh, that doesn't look right, because we said the block weighs 40 newtons, so that's bad, because that should be a 40, and I can see that I multiplied it wrong. So it looks like it's going to be 4 times that are probably 20 newtons. Yeah, it's going to be 20 newtons. So let's fix that. 20 newtons. Okay, and that concludes our lecture. Good luck with the problems, and we will get back together and go over them when we can.